So we had gotten probably about 7/8 of the way through the chapter for acids and bases, and only have just a little bit left to cover, which will then make homework due for the acid base chapter on Thursday at midnight. And I will also see the other half of you for lab tomorrow night. Last week we did equilibrium constant, and so the other half of the class gets to do equilibrium constant this week, and hopefully that will get us all back in track for the sort of after spring break concept of things. All right, let me share screen. So the last things we were talking about pre to the test were a little bit about some other ways you can get acidic and basic solutions that are not directly related to adding an acid or a base to the water, but are more related to adding salts. So I want to kind of like backtrack just a little bit here. Ammonia, we know, is a base, but it's a base from the reacts with water point of view to give you hydroxides. Well, what if you took the conjugate acid part of your NH3, which is your NH4 plus, and dropped that in water, and it will react with the water, because this is all about the trading around of protons. So it will ditch one of the protons that it had. Instead of being NH4, it now migrates back to being NH3. But then the proton will hook to the water molecule, and you will get H3O plus, which is your not shorthand version of indicating that you have acid present. The other two that I mentioned a little bit here at the end of class on Thursday last week was highly charged metal cations. Highly charged usually means at least +2, but often means +3. And so I picked on iron and aluminum as two really decent examples for making this work. And we're kind of harking back to that whole coordination compound idea, because all of the molecules that are being produced are compounds that have charges, and it's often charges that involve the presence of ligands. That's especially true of the second one there that involves aluminum. But even with the iron +3, if you react it with water molecules, it will, we'll call it facilitate, the swapping of a hydroxide from one of the molecules of water, and then taking the leftover hydrogen and sticking it to the second water molecule. And that's where your H3O plus comes into play. The aluminum very definitely has obvious ligands there, because we've got 6 water molecules attached. And by the time you disassemble one of those 6 water molecules, that you have 5 complete ones left over, but there's one that you've torn in half and it has an OH left. The remaining hydrogen goes to a water molecule that is present in the beaker with it. Both of those give you H3O pluses, just like the NH4 did. So a lot of this is really dependent upon looking at your Kas and your Kbs. We know that Kas and Kbs are a feature of weak acids and weak bases, such that Kas are a way to give you an idea how strong your weak acid is. But KBs do basically the same thing. If your KB is stronger, bigger, it will give you a basic solution as opposed to an acidic solution. So you need to look at your Kas and KBs. How are they in comparison to each other? If they're really close in value, close doesn't necessarily mean they have to be 7.0 times 10 to the negative seventh. It might actually be something a little bit different than that, like, I don't know, 6.8 to the negative seventh or something along that line. Chances are you will not have enough ions generated to really change your pH. All right, moving on to the last couple of topics then in the chapter. So one of the things that allows you to have a level of prediction in terms of behaving as an acid. How strong is the bond? Basically, how easy is it for you to tear off the hydrogen so that it can go react with something else? But also polarity. Remember, polarity kind of relies upon where on the periodic table your element is. So I picked on 4 not oxygen, so non-oxy acids here. We've got HI, HBr, HCl, and HF. If you think about how they fall on the periodic table, when you look down that column of halogens on the periodic table, you will see that iodine is the one that's closest to the bottom, which also means that it has the lowest electronegativity of those 4, I, Br, Cl, and F. And then as you are going up toward the corner where fluorine is, and we know that fluorine is the biggest value possible in terms of electronegativity. So this affects how your hydrogens fall off, okay? Your hydrogen and iodine gives you hydroiodic acid. That one actually is going to give you a relatively strong acid because there's a big polarity difference in terms of I versus H. Well, then going down the values, but up the table, we have HBr as the next one up the column. So hydrogen is going to hang a little tighter to bromine than it does to iodine. Going further up the column, we have HCl. That one's the one that we see all the time. HCl is a known strong acid. But then hydrogen and fluorine, there's not as much of a bond strength because it's more polar, okay? You have this whole idea of being able to hang your hydrogen and your fluorine together, so it's going to make it more polar than your HI. So we can make predictions, okay? We can make predictions based upon strength and polarity. The other piece to this puzzle is the oxy acids. More oxygens gives you more polarity and makes it easier for your hydrogen to fall off. Also, back to the electronegativity thing. So HCl, so we have a higher value for the electronegativity, means that it's going to be a little more polarized. Okay, so HClO4, again, we're harking back to one of those known 4 strong acids. HBrO4 is a little wimpier. The other thing you can compare here is your number of oxygens. And I watch too much like crime drama. It used to be CSI, and then it was CSI for a while. And or NCS for a while, and there's some other things that are kind of related there. If you want to dissolve a body, okay, nitric acid, HNO3 is a good choice. So is sulfuric acid, H2SO4. On the other hand, nitrous acid, HNO2, is not as powerful. You have fewer oxygens. It is a weak acid in comparison to the nitric. Sulfurous, H2SO3, is a weaker acid than sulfuric, the H2SO4. So a couple of different ways to make predictions here that involve how many oxygens, involve electronegativity, involve where things are on the periodic table that affects your bond strength. All of those pieces kind of play into this in terms of being able to make predictions about strengths of acids. Now, the very last segment of this chapter involves the most, I'll choose the word expansive, or the broadest way to talk about acids and bases. Now, we did Arrhenius at the beginning of the chapter, and then we did Bronsted-Lowry. This third version is known as the Lewis acids and bases. Now, this time around, we are not trading hydrogens or naked protons. We are trading electron pairs. So this makes it an awful lot more like the ligand concept. If you look at a Lewis acid definition here, we have an electron pair acceptor. Okay, so if it's going to accept electrons from something else, chances are that means it doesn't have a lot of electrons on its own, a lot of electrons to potentially give away. So it would be more likely to gather them up from another source. Your Lewis base is an electron pair donor. So it needs to have at least enough electrons to be able to part with some. So things that have enough electrons to give them away are going to fall in the Lewis base category. But unlike a more traditional Bronsted-Lowry version, where either you're trading a proton, or if you go back to the Arrhenius version, acid and base gives you salt and water, this time your product gets referred to as an adduct. And it is a combination of things. So if I take my F minus, so the minus there is part of your tip off that it has a full octet and it parting / sharing its extra electrons is what makes it a base. If you were to draw out BF3, you would notice that it does not have any extra electrons. So let me flip back over to my whiteboard here and kind of show you what we're talking about in terms of Lewis structures here. Okay, Lewis structures and Lewis acids and bases are all related because the structures tell you more about it. Remember that boron is the weird one. Boron is the one that, under most usual circumstances, boron doesn't like to actually have a full octet. Boron is pretty happy with just 6. So if I put 3 fluorines around it, and I actually go through and we'll see how cooperative my little drawing tool is here. All right, we need 6 electrons around each of my fluorines. That way, all of the fluorines actually have their own octet. It's just the boron that doesn't. So here's your BF3, okay? Note, okay, remember the atom in the center of the molecule is basically the one in control. It doesn't have any extra electrons. It's got the ones that are part of the bonds. It's got the 3 legs, but there's no extra electrons. So this kind of reinforces the idea that it is the one that is going to be capable of accepting. So let me switch back over to my other file here. Once you have everything glued together, once you have F- and BF3 together making the adduct, now you've got BF4 plus, and there is no second product. There is a single product when you're doing this. What about silver and ammonia? Okay. Ammonia, we know from Lewis structures. Ammonia has a nice little lone pair that sits on top of the nitrogen. Hydrogens never have lone pairs. And the ammonia will become attracted to the positive charge of the silver, and you get a ligand situation there. And actually, I realized that I've like hosed something here. I put the wrong subscript in there. Okay, it's supposed to be silver, ammonia, and the plus on the outside, because I didn't ditch my hydrogen. Actually, the hydrogen is still there. I just realized that I had not put the right subscript in there. What about copper? Copper is another metal that we have seen in the past as being attracted to the lone pairs that are on ammonia. And so you can have the acid-base reaction going there, and you have the 4 ammonia molecules being attracted to the copper. So all of those pieces kind of fit together. Drawing the Lewis structures is a really good way to kind of help you predict. Let me go back over here to the whiteboard a minute to talk about the ammonia. All right, N, we have 3 H's, 1 for each leg. And then your 2 electrons are going to sit there on top. And that gives you your lone pair that can become attracted to a metal. It's almost always metals, almost being the qualifier there. Boron is not a metal, even though the boron is in the center of that one molecule. It functions in certain ways that allow you to help make the adduct. But most of the ones that you are likely to see often have a metal that reacts with something that has a ligand. So kind of keep that in mind in terms of homework things. And that actually gets us all the way to the end of the chapter. So actually, let me open up my homework file and talk about that for a moment before we move on to the next chapter. All right. All right, this is acid-base homework. The first couple are very much focused on use of the square, the pH and POH and H plus concentration and OH minus concentration, and how if you know one part of that square, you can always figure out the other three parts. So that's kind of the focus of the first two there. For number 3, this one uses the standard ideas of equilibrium such that you know what your Ka value is, you can solve and figure out what your concentrations are of the unionized ones as well as the ions, meaning the H plus and the A minus, and calculate percent ionization. So there's basically 4 answers to that. You have unionized or non-ionized, and you have both the H plus and the formate ion, and then you have the percent ionization. Then we have some conceptual stuff here that involves the weak acids and the strong acids. I gave you some information. There's also some information covered in your textbook. Then we kind of go around the circle a little bit back to equilibrium, but this is based on knowing the intro or the initial concentration, but you need to find pH. And the last chunk here involves the acids and bases from the Lewis point of view. All right, so homework will be due on Thursday night. Questions? All right, back to my files again. One of these days I'm actually going to get all this sorted out, all this stuff sorted out in the right set of folders, so I don't have to hunt quite so much. All right, moving onward. We are going to take a lot of the information from the acid-base chapter and sort of continue it forward and a little sideways also to apply it in some additional ways. They refer to this as the common ion effect. So most of the things that we've looked at so far this semester in terms of equilibrium have been things that only have a single solute in your solution. You took one thing, you dissolved it, that was the only thing that was there. Usually ended up with something that was positive, something that was negative, and then probably an unionized version. But it was all based upon a single type of molecule. What if you have more than one? What if you have 2 solutes, but they're cousins? They have something in common. So I'm going to pick on, okay, and this is me kind of doing the biochemistry thing. So AC, capital A, lowercase c, is in the world of biochemistry is a shorthand for acetate. And I am very guilty of this because I find it a lot easier to write it. So I tend to use it as a shorthand a lot, but let me kind of go back to this. So capital A, lowercase c, and usually given the minus there, is, so it's acetate, which we've seen quite a lot of, and we know can be written a couple of different ways. We've got the version that we see a lot in the first semester, which is this one, C2H3O2, and it has a minus. But then since we did all of the organic stuff back at the beginning of this semester, you also see it as CH3, and you have the C that has the double bonded O sitting on top that also has a single bonded O, and there's a little minus over here. This is your negative charge. So I forgot a bond. There's my missing bond. So all of these things mean the same thing, okay? AC minus, like I said, this is a biochemistry kind of shorthand for it. And then acetate as a word. Then we have the kind of standard inorganic looking version of the formula. And then we have a structural formula. They all mean the same thing. All right. So what if you had sodium acetate, which is a salt, mixed with acetic acid? I actually didn't mean to make my C right there a capital. So sodium acetate, being a salt, dissociates pretty close to 100%. We've seen a lot of acetic acid. We know that acetic acid is one of the weak acids, which we also know means it doesn't dissociate super well. You're going to have a lot of it still in its unionized form, and only a portion of it is going to split apart into H pluses and acetate minuses. So think about some of the things that we talked about in terms of Le Chatelier's. So look at that look one line back, okay? If we look here at, kind of highlight this one here. If we look back at that one, if you added some extra acetate, well, you're pushing on the right-hand side, so the equilibrium will shift to the left, which also means it's going to decrease your H plus. It'll make your pH more basic. Maybe not super basic. It's probably not going to get it up to 14 or anything like that, but it's going to make it more basic. So this is referred to as the common ion effect. Shift your equilibrium because you dumped something else in to an already dissolved substance, and they had something in common. In this case, it's the acetate ions that are the common effect. All right, we're going to approach this from a couple of different angles here. If we have 0.4 acetic acid and some 0.2 sodium acetate, I'm going to put them all in a beaker together, stir it up, figure out what the pH is. Well, my acetic acid, this is another number you kind of see quite frequently, has a Ka of 1.8 times 10 to the negative fifth. That, like I said, you see this one pretty frequently. And I'm going to write my equilibrium expression. I'm going to put my two ions on the top, and I'm going to put my unionized version on the bottom. But instead of having a number and a 0, this time around, I already have some acetate present. So look at the top line of your ice chart there. I've got 0.4 of the acetic acid. I have no known H plus at the beginning, but I have some 0.2 of the acetate. So then you have to think about, okay, which direction are we pushing this? Well, a little bit of your acetic acid, not a huge amount, but a little bit, is going to fall apart. So that's going to give me the negative X on that left-hand column there. But it will give me a small amount of H+. It will also give me a little more acetate than I started with. Because I started with 0.2, it's going to bump up a little bit. So look at your equilibrium line. I've got 0.4 minus X, I have X, and I have 0.2 plus X. Now, none of these are actually undoable from the whole crunch and slog your way through the quadratic equation. You could actually do that because you would have an x squared, a bx, and a plus c. But I'm going to shortcut this one. I'm looking at my values of my concentrations. So here up in the acetic acid, it's 0.4. Remember, if you did this in scientific notation, that would be 4 times 10 to the 1. Actually, 10 to the negative 1. Negative 1, not positive 1. Same idea for this one, okay? If I have 0.2, that's 2 times 10 to the negative 1. Look at your Ka value. Your Ka has a 10 to the negative 5th exponent. So that's 4 orders of magnitude, 4 exponents worth of difference there. I'm probably okay in doing an approximation. So I'm going to delete the plus X and the minus X from my equilibrium line. And so you can see where I wrote it one way first, and then I approximated it to do my shortcut. I originally wrote it as X and 0.2 plus X on the top and 0.4 minus X on the bottom. So I'm gonna delete the ones that are added and subtracted. You do have to have an unknown, so you can't delete the other X. However, that does make the math for finding my X a bit more straightforward than having to slog my way through the quadratic. And as I go down through this, I end up with a X value of 3.6 times 10 to the negative 5th. And it did ask you what the pH was. So negative log of, and I have a pH of 4.44. Kind of makes sense, okay? I had some acetic acid and a little bit less sodium acetate. And I dumped them all in the beaker together. It's acids and pretty wimpy conjugate bases. So it kind of makes sense that my pH ends up on the acidic end of the situation, as opposed to ending with a pH like of 9 or 10. All right. Extending this idea. Buffers. Buffers are actually kind of what were in the previous problem there, even though we didn't call it that yet. A buffer is a weak acid or a weak base plus a salt. They have to share an ion. Why do you want a buffer? Well, you want a buffer so that you can make it harder for pH changes to happen. Buffers have an acid part such that if you dump a little hydroxide in there, it kind of absorbs it. But then they also have a conjugate base present, so that if you dump a little acid, a little H plus in there, it also absorbs it. All right, let's look at the 3 that are most common. So there's the one that I already showed you there on the first page, that is usually acetic acid mixed with, it can be either sodium acetate or potassium acetate. It doesn't really make a difference what your ion was there in the front. Sodium and potassium are usually the most common. there's phosphoric acid combined with biphosphate. Look at that second one there. We've got a phosphoric acid molecule that basically lost a hydrogen. And then the bottom one of those three is the one that is in your blood. Okay. If your blood changes pH much, you have a lot of problems. Okay. So bicarbonate, which is HCO3 minus, and carbonic acid. If you put these all together and you are talking about a biological system, mammalian blood, you usually end up with a pH value somewhere in the neighborhood of about 7.2 to 7.4. I know that doesn't sound like a very big bracket, and it's not. Okay. The human body doesn't function well if your pH gets below about 7.15. You get ketoacidosis. On the other hand, there are other things that can happen that would raise your blood pH, things like liver failure, that would give you a pH maybe above 7.5. Again, bad for human bodies. So there's lots of biological relevance to that last pairing there. In chemistry, however, in general chemistry, we tend to pick on the first one the most frequently. I'm going to do this first example that makes an assumption that what you are adding to it does not measurably change your volume. This is probably somewhat unrealistic. We'll call it an idealized situation. So let's take some 0.05 molar acetic acid and some 0.05 molar sodium acetate. We want to add a little hydrochloric acid. Putting hydrochloric acid in just water drops your pH drastically. Putting hydrochloric acid in a buffer probably drops your pH a little. All right, so let's look at this from a couple of angles here. We're harping on acetic acid. 1.8 times 10 to the 5th is your Ka value. And I put my two ionized versions on the top, H plus and AC minus, put my unionized version on the bottom. And I assume that because I have identical acid and salt, weak acid and salt, I can take the P of the Ka. Okay, remember I said P is a function. P means take the negative log of something. Okay, and if I actually go back, and it occurred to me that this is where I run into these problems again of things that I normally write all over the chalkboard, or actually these days it's a whiteboard. I don't always have put into my notes. Let me kind of add a line here. Let's do, so negative log of K and my Ka value, actually we'll do 1.8 times 10 to the negative 5th. All right, and so that gives you the 4.74. All right, so if I have my buffer and I have not yet done anything to it, I have a pH of 4.74. Then I'm going to add that little dribble of hydrochloric acid. So this is when I start needing my ice chart. Note, the problem said a liter, so 0.05 molar times 1 liter gives you 0.05 moles of the acetic acid. I have 0.05 moles of the acetate, but I have 0.003 moles of my hydrochloric acid. Stir it up, okay? Because I am using the Le Chatelier concept here, that little bit of H plus is going to latch on to the AC minus and backpedal toward the left-hand side of this equilibrium. So that gives me minus the 0.03 that I added, minus 0.003 of my 0.05. It's going to give me a little extra HAC. All right, look at the equilibrium line here. So once I've totaled this down, I have no H plus extras left over now. Doesn't mean there's none there. It just means that there's no extras. So Ka didn't change, 1.5 times 10 to the negative fifth. My X is my H plus, but I'm now going to consider my AC to be 0.047 because it's less than it started. My HAC went up a little, 0.053. Crunch out your little data there. I get an X value of 2.03 times 10 to the negative fifth. Do your negative log of. I dropped my pH a little bit, okay? So look at my comment there. If you put 0.003 moles of hydrochloric acid in some distilled water, you get a pH of 3. So that's getting way down there. Adding it to a buffer will change your pH, but only by a small amount. I went from 4.74 to 4.69. That's not a big difference, okay? That's a pretty small change in the world of pHs. It did change, okay? It's not that nothing happened. It's just that not a lot happened. And that's kind of the purpose of the buffer. The buffer is to prevent your pH from getting crazy high or crazy low if you are setting up a scenario for keeping your proteins happy. All right. What if we did change our volume? So let's take a look at this one. This one's kind of done in phases. Slightly different buffer setup here. I've got 10th molar acetic acid and 10th molar sodium acetate. Set up my ice, and actually I left out the C. Yeah, there's no middle line here. When it was all by itself, and I haven't added anything yet, I just have my buffer. I've got the 0.1 for the HAC. I've got the 0.1 for the acetate. At the end, I've got 0.1 minus X, and my acetate's 0.1 plus X. And I shortcutted it because it was 4 orders of magnitude difference. And note, yeah, I do actually get the same number. Okay, I get the same number from the previous problem, 4.74, because matching amounts of acetic acid and sodium acetate will always give you 4.74. It is in the nature of that particular buffer. If you use those two substances, acetic acid and sodium acetate, and they have matching concentrations, it will always crunch out to give you a pH of 4.74. But this time I'm going to add some sodium hydroxide. Okay, so start with the idea that, oh, sodium hydroxide's a base. This is going to make my pH go up. Now, granted, probably not a humongous amount, but it will go up because I am adding base. This time around, I have a little more information. I know how much sodium hydroxide I'm adding. I'm adding 2 mils, but my buffer has a volume of 100 mils. I need a little more number crunching involved here. First thing I'm going to do is figure out how many moles of base I'm adding. So volume, 2 mils is 0.002 liters times 0.1 gives me 2 times 10 to the negative 4th moles. I have a 1/10 of molar of acetic acid, and I have 100 mils of it. So 0.1 times 0.1 gives you 0.01. And I'm going to use up / cancel out a small amount, 0.0002. That means I have 9.8 times 10 to the negative 3rd moles left. But I also changed my volume a little bit. The volume is no longer exactly 100 mils. It's now 102 mils. Make sure you're putting this in liters to make sure everything cancels out correctly. So 0.102. My concentration of my acetic acid dropped a little bit. But Le Chatelier still works. Because I used up a little acetic acid, it also makes a little sodium acetate. It makes the amount that matches the sodium hydroxide I added. So I have 0.01 moles of acetate. 0.1 times 0.1 because it's 0.1 molar and I had 100 mils of it. I'm going to add 2 times 10 to the negative 4th to this one. The sodium doesn't make a difference. It's just the acetate I'm worried about. This time I have 0.102 or 0.0102 and 0.102. Even though I changed the volume, I also made a little more stuff. I made a little more sodium acetate. So I actually end up with the same number again because those two things kind of canceled out. Doesn't always happen, just happened to for this example. Plug everything back in. Okay. I know I want my pH or expect my pH to go up. So I crunch through my data there. I put my Ka in. I put my my X and my 0.1 and my 0.096 in. My X comes out to be, instead of 1.8 to the negative 5th, it's 1.728 to the negative 5th. Negative log of, I get 4.76. It did go up, just not very much. Sometimes you will not see a very big change, but it should match in direction. with what you are adding. If you added acid, things like hydrochloric acid, your pH should go down a little bit. If you add a base, your pH should go up a little bit. So let's look at it from the kind of conceptual point of view here. So if you are taking hydroxide, because the sodium doesn't really matter, and you're adding it to the HA part of your equation there, you get A minus, so whatever the ion is, plus a little water. The hydroxide reacts with your unionized. Okay, it doesn't just dangle around in solution. The OH actually does a reaction. But because it follows Le Chatelier's, it's going to change the pH and change the concentration of things that are on the right-hand side. More conceptual idea going back to the first example there. If I add an acid, it will react with whatever the negative ion is to give me unionized acid, HA. So one pushes it in one direction. If you add hydroxide, you get more A minus. If you add H plus, you get more HA. Those are kind of like from the conceptual point of view. There is an alternate way to do this, but it really only works from the point of view of what's the pH of your buffer, but doesn't work well in terms of adding things to your buffer. More famous dead guys, Henderson-Hasselbalch. So the pH of your buffer is pKa, because remember, P is a thing. P means take the negative log of something, plus log of conjugate base over acid. If I've got 0.4 and 0.2, this goes all the way back to the very first example there that I was doing. You can get the same answer, different methodology, but it still gives you the same results. I had 0.4 molar acetic acid and 0.2 molar sodium acetate. I did, oops, I just suddenly realized I have a negative sign missing. There's your negative sign. So negative log of 1.8 times 10 to the negative fifth. And then log of 0.2 over 0.4. You have to put the salt part of your acid salt buffer on the top. Otherwise, you don't end up with the right answers. So my suggestion is divide before you take the log of. So divide 0.2 by 0.4 and then take the log of it. And that will give you negative 0.3. 4.74 minus 0.3 gives you 4.44. If I scroll all the way back up here, this is exactly what we were looking at here in the beginning, okay? We did it kind of the longhand method at the beginning of this portion. But if the only thing you're interested in is the pH value, you didn't add extra stuff to it, extra acids or extra bases, you can use Henderson-Hasselbalch to help you figure this out. Okay. We can even do it some alternate versions, which I don't really want to get into tonight. But if you look at the notes file later for this, we are going to continue with a variation on this theme that allows you to tinker with the Henderson-Hasselbalch and figure out base buffers. There's another step involved if you're using a base. Otherwise, you end up with very bizarre and wrong answers. But there are ways to compensate for this in terms of how you rearrange it. All right, that gets us a ways into the buffer KSP chapter. Some things that are up and coming in lab. Yes, tomorrow night is equilibrium constant for the other group. And then next week, we are going to do a pH titration. We're going to use the pH meters, and you are going to create a titration curve for a diprotic acid, which is, I will go ahead and tell you, it is long and tedious because you are going to need to graph about 70 data points in order to get a curve that has the right kind of inflection points on it. So this is something that is up and coming for the following 2 weeks. After we get done with that, then I think the last physical lab of the semester involves titration and KSPs. So we are past the halfway point. We have about 6 weeks, because the very last week of the semester, there are no labs. That is just turn stuff in and final exam stuff. Keep in mind that the final Monday of the semester, which, let me grab my phone so I'm telling you the right date on this. I believe it's the 3rd, but let me double check. The 3rd of May. Yes, the 3rd of May is the last Monday of the semester. So if you have me for lab, everything that you turn in for lab has to be turned in by midnight on Monday, May 3rd, because I need 2 days to grade stuff and get it to other professors, or to be able to roll it into final grades. And some people have been turning in some of their back work from lab stuff, which is great. However, there's still a lot IMO'd, so keep that in mind. You are running out of time in order to be able to get all those things turned in. Questions?
I have a question.
Yes.
So I missed out on lab last week. Is it okay if I come in tomorrow?
Yes, we are doing the same thing tomorrow that we did last week. So yeah, that should be just fine.
Okay, thank you.
Because yeah, I think I only have, because 2 people dropped, I think I only actually have 12 students total, but I don't want to mess with the group at this point and try to have everybody come in at the same time. I'm just going to leave it as A group and B group because it gives us a little bit more flexibility anyway. All right, I will see some of you tomorrow night.